And please do ask questions, because otherwise with Zoom, you go way too fast. I go way too fast and run out of material. So let's suppose we have a symplectic manifold with a Hamiltonian action of a Lie group, compact Lie group K. If the stabilizers are all finite, then the cross section is defined as the preimage of the Lie algebra of the maximal torus under the moment map. The cross section identifies one element of each orbit under the group action. This is no longer true if the group action has infinite stabilizers. The imploded cross section is defined as the quotient on each stratum by the commutator subgroup of the stabilizer of the action on that stratum. So the universal example of an imploded cross section is defined as the imploded cross section of the cotangent bundle of the Lie group. And we can look at some invariants of imploded cross sections. In the simplest case, SU2, the universal imploded cross section is just C2, so its topology is trivial. So we were looking at the next case, which is SU3. And there, the universal imploded cross section contracts to a point, but we compute its intersection cohomology, which is not a homotopy invariant. We find that this invariant distinguishes it from the intersection cohomology of a point.
Sorry,
Yes.
and how come that commutator subgroup enters the play?
I will get to that. The reason is that the cross section turns out not to be symplectic. The preimage of the Lie algebra of the maximal torus under the moment map is not symplectic. And in order to define something where the strata are symplectic, what you have to do is quotient by the commutator subgroup on each stratum. Then you get something that is not actually smooth, but it's a stratified symplectic space. So I'll get to some examples. Intersection cohomology is a topological invariant. So if you have two spaces that are homeomorphic, then they have the same intersection cohomology. But it's not a homotopy invariant. So two spaces that are homotopy equivalent would not necessarily have the same intersection cohomology. Let me go back to the definition of intersection of the imploded cross section. So
sorry, could I just ask a question about that? So so I'm not very familiar with intersection cohomology, but it's some cohomology theory for stratified spaces. Right? So is there any homotopy invariant such construction? Or is there some reason why you shouldn't expect there to be some homotopy invariant?
Intersection cohomology is not homotopy invariant. There is another construction called homotopy intersection spaces, which I will talk about later due to Banagel and Hunziker. And those are, write this down. Banagel, Hunziker. I should say these spaces, defining these spaces requires stratification and various other choices such as perversities, but in some cases, although you need to specify these things to make the definition, the result turns out to be independent of the choices.
Thank you.
Okay, so let me go over the definition of intersection of imploded cross-section. Again, if K is a compact connected Lie group, maximal torus, the maximal torus is T, the Lie algebra is boldface T. And let me put T plus as the fundamental Weyl chamber. Let's let M be a Hamiltonian K manifold, and I'll denote the moment map by phi. Then the preimage of the Lie algebra of T under the moment map is not smooth in general, and it doesn't decompose into smooth strata equipped with symplectic structure. That's the purpose of defining the imploded cross-section. This definition was made in a paper myself together with Gilman and Shyamar. So we define the imploded cross-section by taking the preimage of the fundamental Weyl chamber under the moment map and defining an equivalence relation so that 2 points are equivalent if by acting by the commutator subgroup of the image of M1 under the moment map, you get from one point to the other. So the imploded cross-section, or the symplectic implosion, is the quotient of your manifold by this equivalence relation. The universal imploded cross-section is the imploded cross-section of the cotangent bundle under the action by conjugation. The symplectic quotient at 0 of the product of a Hamiltonian K manifold with its imploded with the universal cross-section, universal imploded cross-section of the cotangent bundle is the imploded cross-section of the original manifold. That's why we call it universal imploded cross-section. So some examples: universal imploded cross-section for SU2. Well, the cotangent bundle, this is true for any Lie group. Cotangent bundle is the group cross, this should be boldface, cross the Lie algebra. And the moment map is just projection onto the Lie algebra. The preimage of the Lie algebra of the maximal torus is just K crossed with the Lie algebra of the maximal torus. The implosion is given by collapsing the fiber above the identity element by the action of the commutator subgroup. But since K is assumed to be, if K is assumed to be semi-simple, obviously true for SU2, the K is equal to its commutator subgroup. So this action collapses K cross 0 to a point. So the imploded cross-section is just K cross R quotiented by the equivalence relation that identifies all points where the R element is 0, all those points get identified together. So in the case K equals SU2 or S3, the imploded cross-section is just the cone on S3. In other words, it's C2. For SU3, the universal imploded cross-section has the structure given by a quadratic relation. set W where the inner product is equal to 0. And this has an isolated singularity at 0. It's isomorphic to the open cone on the set where you keep the quadratic relation and you impose the condition that you're in S5, you're Z squared plus W squared is equal to 1. So that this description appears in the paper with Guillen and Chiamar in section 6. And I will describe how you use this using my Retraction sequence to compute the homology of this space Y, and that enables you to compute the intersection cohomology of the original space. This should be X. So this space, the SU3 space, has an isolated singularity at 0. It's also possible to describe imploded cross-sections of quasi-Hamiltonian spaces. Quasi-Hamiltonian spaces were defined by Alexeyev, Malkin, and Van Rankin, 1998. The quasi-Hamiltonian K space, K again, a compact Lie group, is a manifold equipped with a K action and a 2 form. The 2 form is not closed and is also not non-degenerate, but it satisfies 3 key properties relative to the K action, which are analogous to the properties that you have to define a Hamiltonian K space. So for a Hamiltonian K space, you would require that the 2 form is closed and non-degenerate, and that there is a moment map. So those 3 properties have analogs in the setting of quasi-Hamiltonian spaces. So the space K cross K is actually the quasi-Hamiltonian analog of the cotangent bundle. And the analog of the moment map is the commutator map. So instead, for quasi-Hamiltonian K spaces, instead of having a moment map which takes values in the dual of the Lie algebra, the analog of the moment map takes values in K. So and K group. Commutator map just means X, Y, X inverse, Y inverse. So it is possible to define an imploded cross-section for quasi-Hamiltonian spaces. Restricting to K equals SU2, the imploded cross-section of the analog of the cotangent bundle, K cross K, is isomorphic to S4. For the spaces, the points where the stabilizer under the conjugation action is the maximal torus, we define that stratum as sigma 0. And
Lisa,
yes, yes.
there is a question on chat
Okay.
from Francois.
Mhm.
So he asked, why do we care about deformation retraction if the theory is not homotopy invariant?
Where did I say that?
That was hello. That was
yes.
two slides ago, I think.
Well, that was to compute. Yeah, the space is not deformation. You care about it because to compute anything about it, one way is to use a Meyer-Vietoris sequence.
For singular homology, but
yes.
the intersection homology, I mean.
It is also possible to use Meyer-Vietoris sequence to compute intersection homology.
Okay, so there's some sort of homotopy invariance on the pieces that can be used?
Yes, yes.
Okay. All right, thank you.
Okay. So there are two other strata, the elements of the center of SU2, which are just the identity matrix and minus the identity matrix. And the preimage of those strata quotiented by K is just a point. And so these things fit together to form the suspension of S3, which is S4. That's rather similar to the construction that we gave about C2, the imploded cross section of SU2. So this is the quasi-Hamiltonian imploded cross section. And there are generalizations of this to SUN, where the Q-Hamiltonian imploded cross sections are copies of S2N. This is in joint work with Jacques Bertubis and Retraction. So I should mention places that imploded cross sections appear in the literature. There is a body of work by Francis Kirwan, Andrew Denser, and Andrew Swan, and some other collaborators around 2013, 2015, about implosion on hyperkähler manifolds equipped with actions of Lie groups. There is also work of Pavel Safronov about shifted symplectic structures, and symplectic implosion appears in that work. There is work by Johan Martens and Michael Thaddeus constructing implosion using symplectic cuts. There's work of Howard, Manon, and Nilsson, 2011, about bending flows in polygon spaces and implosions of those. There is work of Jeremy Lane about symplectic contraction, which does in a sense the same job as some of the constructions in Howard, Manon, and Nilsson's paper. But with rather less hypotheses. And there is recent work of Lane together with Ben Hoffman about collective integrable systems. So symplectic implosion has had a lot of applications in different contexts. As I noted, intersection cohomology satisfies some of the properties of ordinary cohomology, but it doesn't. So for example, you can define, you can prove Hard-Lefschetz theorem, Lefschetz hyperplane theorem, and Poincare duality in the context of intersection homology. But it doesn't have, in general, have a ring structure, unlike ordinary cohomology. This, of course, is, I should have mentioned, Goreski. To define intersection cohomology, you need a stratification. For example, Whitney stratification. But if a topological space has two different stratifications, the intersection cohomology doesn't depend on the stratification. For imploded cross sections, the stratification just comes from the orbit type of the original manifold. To define intersection cohomology, you need what is called a perversity. So perversity is a sequence of integers. You can make a definition where you impose some conditions on the stratification, basically that it is monotonic, and the condition that P of k is less than or equal to P of k plus 1. So the intersection homology of a pseudomanifold or manifold with stratification is the homology of the chain complex of allowable chains. You say that a chain is allowable with respect to this perversity if you impose a condition about the intersection of the chain with strata. So if you were dealing with a manifold, not a singular space, then if the n minus k stratum had real dimension n minus k, and the chain sigma had dimension j, then the dimension of the intersection would be exactly j minus k by transversality. And that would be the value specified by P of k equals 0. So what the perversity measures is basically how far you are away from transversality. This is basically what the perversity is telling you, that the intersection has bigger dimension than you would predict from transversality. So let me briefly describe another construction, homology intersection spaces. This is due to Van Agel and Hunziker. So an intersection space is a pseudomanifold whose depth is 1. The depth of a stratified pseudomanifold is the number of different non-empty skeleta that it has minus 1. So a skeleton you can think of as a stratum. This definition you can find in the work of Greg Friedman. So we can write the stratified space as having, so I'll denote the strata by X superscript K. So there is a large stratum. If you remove X to the n minus 1, then you get a space that is dense in the original space. And for each of these, if there's a point in the I subspace, which is not in the I plus I minus 1 subspace, I minus first subspace, then there is a neighborhood for which there is a pseudomanifold and a homeomorphism with L, pseudomanifold L, which is called the link of X, and a homeomorphism of Ri crossed with the cone on L to a neighborhood, taking Ri crossed with cone on the J minus 1 part of the link to the X plus I plus J intersection with U. So this is a local description of how these strata behave. The xi are called skeleta, and you can denote this complement by x lower I, and then the strata are the connected components of the x lower I. We can define L less than K as the union of all the strata of L that are of degree less than K. And a Moore approximation of the link of the stage K Moore approximation of the link is what you have if the homology groups are 0 up to 0 if for I greater than or equal to K, and isomorphic to the ordinary homology of L for I less than K. A blow-up manifold of a singularity in a space X is defined as you remove the singularity and then you take the union with the link of the singularity crossed with sigma crossed with an open interval, gluing together by a diffeomorphism of the tubular neighborhood of the singularity to the link crossed with the singularity crossed with an open interval. So if we have one of these stage K Moore approximations of the link, let me define by G the map. This is a map from the Moore approximation L less than, or it's from L less than K crossed with the singularity to the blow-up space. So it's just given by the composition of this from this space to, that's just inclusion, L cross L into L cross sigma. That's the boundary of the blow-up space that then includes into the blow-up space. So that's what I mean by the map G. And Banagel-Hunziker defined the perversity P intersection space as the blow-up space union with the cone on the Moore approximation crossed with sigma with an identification using the map G.
Sorry, excuse me.
Yes?
Could I just ask to make sure I understand? So for instance, for a smooth manifold, the depth is 0, and for a graph, the depth is 1?
For the depth for a smooth manifold, you would be talking about yeah, for a smooth manifold, the depth would be 0.
And for a graph, it would be 1.
Yes.
And what is the blow-up manifold for a graph at a vertex, say?
I think that for a blow-up space, you need codimension more than you would have in a graph. In a graph, everything would be one-dimensional. Okay. 1 or 0-dimensional. I think for a blow-up space, you would need higher dimensions than that.
Okay, so I just didn't understand this blow-up space.
Well, blow-up space, I think it is modeled on blowing up a point in an algebraic variety.
Oh.
You remove, so symplectic blow-up, you remove a neighborhood, you remove a point, and the boundary of what you're removing is a sphere, and then you quotient the sphere and turn it into a projective space. So I think that the blow-up manifold is analogous to that. You know, these cones play the same role as the cones on spheres, which are balls.
Okay, thanks.
Okay, so the homology of these homology intersection spaces is given by, if the stratified space has an isolated singularity, then Nagel Hunziker proved that the homology of the homology intersection space is the same as the relative homology of the blow-up space relative to the boundary for low values of J, and it's equal to the ordinary homology of the blow-up space for larger values of J. And this doesn't tell you what happens when J is equal to K. We were able to find a commutative diagram that enables you to, there's a commutative diagram that enables you to compute the dimension of the dimension K homology as well. And what Sina and I were able to do is show that if X is the open cone on the link L and P is a perversity, then the homology intersection space of X has homology 0 for low values of J, and where low is specified by the perversity, and it's equal to the reduced homology of L otherwise for larger values of J. In particular, the homology intersection space of the imploded cross-section of SU3 is the homology of this homology intersection space is the real numbers for J equals 5 or 9 and otherwise equal to 0. Nunn-Koho and I were able to construct the intersection homology of imploded cross-section of SU3. And we showed that it was equal to real numbers for J equals 4 and 0 otherwise. So the homology of the homology intersection space is not the same as the intersection homology in this case. Let me describe some of the properties of intersection homology. If you have an open neighborhood of real dimension 2n in a space with an isolated singularity at x, then this you find in the book on intersection homology by Francis Kirwan and John Wolfe. Intersection homology is equal to the ordinary homology of the complement of little x in U for low values of I, and it's equal to the homology of the ith homology of U for larger values of I. For I equals n, you have the image of the homology of the complement into the homology of U. So in fact, we have the following characterization when you have an isolated singularity. If U is homeomorphic to the cone on a manifold Y of dimension 2n minus 1, then the intersection cohomology is 0 for I greater than or equal to n and is equal to the ordinary homology of Y, ordinary cohomology of Y for I less than or equal to n minus 1. So in the case of this universal example, we use this is the construction in my work with Nanpo Ho. We use Meyer-Vietoris to determine the intersection cohomology of the universal example. So we can write V is the set where norm squared Z plus norm squared W is greater than or equal to 1 minus epsilon, and U is where that set, that norm squared Z plus norm squared W is less than or equal to 1 plus epsilon. So the whole space is given by the union of U and V, and both V and U intersect V deformation retract to Y, which is the set where this Z squared plus W squared is equal to 1. So the universal imploded cross section is the cone on Y. This gives us a Meyer-Vietoris sequence for the intersection cohomology. And intersection cohomology is not a homotopy invariant, so we don't actually know the relation between the intersection cohomology of V and the intersection cohomology of U intersect V, although V retracts to U intersect V. But since these are non-singular, the intersection cohomology of V is isomorphic to the ordinary cohomology of V, and the intersection cohomology of U intersect V is isomorphic to the ordinary cohomology of V. So we have that the ordinary cohomology of V is isomorphic to the ordinary cohomology of U intersect V as a result of the deformation retraction, since ordinary cohomology is a homotopy invariant. So that tells us that the map from the intersection cohomology of U direct sum with the intersection cohomology of V, restricting to the intersection cohomology of U intersect V, that map is surjective, and so our long exact sequence splits into short exact sequences. So this means the Meyer-Vietoris sequence gives something that is where the map into the intersection is surjective. That's just because this is isomorphic to the ordinary cohomology of V is isomorphic to the ordinary cohomology of U intersect V as a result of the deformation retraction. So intersection cohomology is not a homotopy invariant. So the deformation retraction, for the deformation retraction, we use the fact that V and U intersect V are non-singular. So intersection cohomology of V is isomorphic to ordinary cohomology of V, and same for U intersect V. The ordinary cohomology is a homotopy invariant, so we can use the deformation retraction. So we wind up with short exact sequences from which we're able to compute the intersection cohomology of U union V that's equal to the ordinary cohomology of the intersection cohomology of U. And same, the intersection cohomology of V is isomorphic to the intersection cohomology of U intersect V. So we find that the intersection cohomology of U union V is isomorphic to the intersection cohomology of U. And the space, the imploded cross section of the universal imploded cross section of SU3 is homeomorphic to U. So I talked about that. Ultimately, we find that the ordinary homology of Y and the ordinary homology of zeroth homology of Y and fourth homology of Y are isomorphic to the real numbers, and all the rest of these are equal to 0. So you could say that the space Y is the disjoint union of two copies of the 5-sphere and a 9-dimensional space which retracts to SU3. The space U is homeomorphic to the cone on Y. The real dimension of Y is 9. So let me finish with some of the references. The reference to the paper that I have with Nanquo Ho is this one. The papers by Benagel and Benagel-Hunziker are these ones. And I mentioned the work of Denser and Swan. There are more papers on these subjects. This is my paper with Gilman and Shamar. This is the paper of Ben Hoffman and Jeremy Lane. This was the later paper of myself with Jacques Hurtubise and Rea Shamar about group-valued implosions. And the book of Francis Kerwin and John Wolfe. Which reference on intersection homology. So I'll stop there.
Great. Thank you very much, Lisa.
Το σχήμα είναι στα
Question? Are there questions?
There was a question, maybe.
Mm-hmm.
It is time for questions, so please go ahead.
So I had a question, but I just think I didn't quite catch something you said. You said that intersection cohomology was something to do with measuring some failure of transversality for the stratification?
That was, let me go back to that slide. What I said was that perversity is a measure of is a measure of failure of transversality. You wouldn't expect. Find that slide. You wouldn't
fail too much. It only failed by one.
You wouldn't expect. Okay. Okay, this is, yeah, so perversity, intersection homology is you define a chain complex of allowable chains where allowable means that the intersection of the chain with the n minus k stratum has dimension j minus k plus the perversity p of k.
I see.
Where if the stratum were actually transverse to, if sigma were actually transverse to xn minus k, then this dimension would be j minus k, which would be consistent with the perversity being equal to 0.
And then given a perversity, what does the intersection cohomology measure?
It measures the homology of the chains that satisfy this allowability condition.
Right.
Yeah, how far you are away from transversality. But intersection homology does satisfy many of the properties of ordinary cohomology, such as Lefschetz hyperplane theorem, Poincare duality, hard Lefschetz theorem. It does not have a ring structure.
I see. So
and
yeah,
there are actually some cases. It's very interesting to identify whether the intersection cohomology of a singular space does have a ring structure. There are some cases where it does have a ring structure.
and it's this
But
relation.
it doesn't in general. Sorry?
Oh, no, sorry. So and I was just going to ask, and it's precisely this relation here to transversality that makes it not homotopy invariant. Presumably.
Yes, I suppose you could say that.
Okay, and then the other one, the intersection.
Homology intersection spaces.
Right, and then so then how should I think about that one? What does that one measure?
Well, these are actually spaces. The homology of them. I think if you started with a smooth manifold, then you would get back the original smooth manifold.
Okay, and if it's singular, kind of how does it differ from say standard singular homology or from intersection homology?
Well, the examples show that if you we were able to compute in this particular example that the homology of the homology intersection space associated to the imploded cross section is not the same as the intersection homology. I think for particular examples like cones, you maybe would not expect that the homology intersection space would be the same as the intersection homology. I mean, cones are the particular case that we were studying was a cone.
Okay.
Sina and I were also computed suspensions, because the construction for cones generalized almost very directly to suspensions, and so we do have some results on suspensions.
Okay, and in terms of standard singular homology, can I think of it, or maybe this is what it is, and you said it, but it's something like the singular homology of the space I get by inductively blowing up all of the singularities.
Yes, exactly.
Thank you very much.
All right, so let's see if there are any other questions for Lisa.
And how this story is related to quantization?
I believe that there has been defined geometric quantization. Actually, I'm not sure that anyone has defined the geometric quantization of the imploded cross sections. That would be an interesting thing to investigate. But I don't think it has been.
All right. So okay. So more questions, maybe. Okay. If not, let's thank Lisa again. So thank you very much, Lisa, for your talk.
Thank you.
So I will post the slides very soon. So you sent me yesterday some slides. In case you want to send something updated, you can.
Yeah, I will. I will.
Yeah, great. Thank you very much.